When diluting a highly concentrated, dangerous acid, you have to mix it with water, but you cannot simply mix them together however you please. You might think it doesn't matter if you pour the acid into the water or the water into the acid. After all, they are just two liquids. Shouldn't the resulting mixture be exactly the same either way? But inside a chemistry lab, there is a strict, non-negotiable rule for diluting concentrated acid. You must always add the acid to the water. Break this rule and pour water into a concentrated acid, and the liquid instantly boils, violently erupting from the container. A student making this mistake faces a sudden barrage of boiling chemicals splashing across their skin, accompanied by the concussive shrapnel of a glass beaker bursting under the intense pressure. You are mixing the exact same two liquids, so why does reversing the pouring direction transform a routine dilution into a face-melting explosion? In a laboratory, everyday intuition is a liability. Survival depends entirely on understanding the invisible thermodynamic laws governing how these liquids interact. Mixing concentrated acid and water creates what is called an exothermic reaction. The chemical interaction itself generates a massive, instantaneous spike of thermal energy. To see exactly how this reaction triggers a catastrophe, let's freeze time on a large volume of concentrated acid, just as a single drop of water falls toward it. The extreme heat generation happens the millisecond they touch, but it remains localized exactly where they meet, at the surface point of contact. This creates a lethal volume mismatch. That tiny drop of water is suddenly forced to absorb all the localized heat generated by the vast pool of acid reacting beneath it. The temperature of that single water droplet shoots past its boiling point in a fraction of a second, converting the liquid water into flash steam. As that steam rapidly expands, it acts like a microscopic explosive charge detonating at the surface, blasting the surrounding concentrated acid outward into the air. Pouring water into acid creates an inescapable thermal trap. A tiny amount of water is forced to take on an unsurvivable amount of energy, and the only place for that energy to go is out. Now let's invert the conditions to follow the correct protocol. We have a massive volume of water and a single drop of concentrated acid falling into it. Upon impact, the exact same exothermic chemical reaction occurs. The total amount of heat released at the surface is identical to the explosive scenario. But this time, we have a thermal heat sink. Instead of trapping the energy in a tiny droplet, the heat radiates outward, dispersing deeply into the massive volume of surrounding water. That large body of water safely absorbs and dilutes the thermal energy. The heat is spread so thin so quickly that the temperature at any single point never reaches the boiling threshold. The acid into water rule relies on manipulating volume. You ensure that dangerous energy is immediately smothered by a massive heat sink before it has the chance to cause physical harm. Setting up that heat sink is only the first step. The speed of the addition is equally critical. You have to add the acid slowly, drop by drop. And as those concentrated drops fall into the water, there is one final physical requirement to ensure safety: constant active stirring. Stirring forces the liquids to mix mechanically. It forcefully disperses the newly generated thermal energy throughout the entire volume of water, preventing any localized hotspots from forming near the surface. Combining a slow pour with constant stirring ensures extreme thermal management. The exothermic heat is generated slowly enough that the cooling capacity of the moving water easily outpaces it. The order, speed, and kinetic movement of a pour dictate the physical reality of the reaction. These mechanical choices are what transform a guaranteed explosion into a routine, safe dilution.